All right. Efficiency. Yeah, you've done these. Some of you have done these a lot. So we use eta, and it's the desired output over the required input. The overall efficiency is the efficiency of one set of objects times the second one and third one and so forth. So like if you have a generator hooked to a turbine, you'd have two efficiencies to find the total efficiency. Eta, yep. So again, if you have a generator hooked to a turbine, okay, basically you have efficiency of the turbine and you have the efficiency of the generator, and then you can multiply both of those to get the total efficiency of that combined system, all right? So let's look at a couple, let's look at 4 different mechanical devices. Let's look at a fan. Bless you. That's not a good looking fan. Slightly better, but that's all I want to do. Think of it as a fan. Huh? The fan in your room or your dorm, your house. These are streamlines. They just kind of identify how the direction of the flow is moving. Don't worry about it. You won't need to know it now, but I'm glad Ben remembered because we just covered it yesterday, so that's good. We're going to pick 2 points. We're going to pick a point here. Oh, I didn't want to do that. I want to make them at the same elevation. Why do I want to do that?
You can eliminate Z.
Yeah. And the other thing we can do is, if you ever felt behind your fan and in front, which one's moving faster? Front, right? So we typically assume the velocity in the back is 0. For simpler cases, we know it's not, right? It can't be physically. But for engineering terms, we can. And V2 has to be a number. So I'll just put a pound sign. So Z1 equals Z2. So the efficiency of the fan is delta E mechanical of the fluid over the shaft. N. Okay. And this is m dot V2 squared over 2 over the shaft. Because what do we want a fan to do? Push air. We want the fluid to move, right? And what do we need in order to get it to move? We need that shaft to spin. Okay. Well, what is that shaft hooked to? A motor, okay? But we're only dealing with that fan part. All right. So this, if you think about it, remember, this is fluid energy. Think about it for students that have had fluids, it's Bernoulli. All right? Where we cancel the altitude, we cancel V1. So we only have output in terms of kinetic V2 squared over 2 times mass flow rate. These units give you power over how much shaft you need. Make sense? All right, so let's look at a turbine now. What does a turbine do? Yeah, we want shaft. We want the fluid to convert it to shaft, right? So we'll draw a turbine. Flip of a it's like a flan, just a fan flipped. And what are those things called I just drew? Streamlines. And Ben, what are they tangent to? Velocity vectors, yep. So in this case, we flip everything, and we obviously know that the velocity here isn't zero, but we can assume it to get a maximum case. And we know there's a lot of energy here. So think about turbine, all that wind is going into the turbine, spinning the shaft, and then think about there's no wind at the other end. Doesn't happen, but for hypothetical cases, we can think of this. And again, Z1 is equal to Z2. And the equation of the turbine is shaft out over the absolute magnitude, because we're looking at efficiencies, the fluid. And we'll just do the absolute, because you would realize that you get a negative on the bottom. But that's the turbine efficiency. And the last two that I want to look at, that's absolute value, yep, is a motor and a generator. Then we'll do a practice problem. And I forgot to make copies, but that's okay. You'll just have to do a little bit more drawing. Here? Right there? And the generator is the other way around. So we basically have electric and shaft, and they're just flipped for each one. Well, from here on out, majority of the time, I'll post a lot of LiveScribe extra problems for you to look at. If you find that I'm going too fast, too slow, just let me know. But I think we're going at an okay pace, right? Soaking all the information up like a sponge.
what's supposed to be at the bottom of the tank or at the top of the, like the water, the free water?
Right on the top of the free surface. Yep. Point 2 right on the top of the storage tank. So we're going to do a couple sketches after this too. What's that?
What's facing up all the way in the end, that's the one, two.
Z direction, up.
Oh.
So I did assumptions. And I redrew that so it included the pump and the motor. The sketch didn't really show that, right? Think about the motor behind the scenes. It's behind the pump. So I put the motor and the pump on there and labeled assumptions. So no KE, no neglected friction. And we're assuming that the liquid at state 1 and 2 are touching the atmosphere. Those two are the same. All right, so I'm going to separate these. Let's look at the motor and let's do a sketch. I'm going to label the boundary in red and then label our work and power. So we have electric coming in. Then we have shaft going out. So let's look at the motor. We know we have electric power coming in, and that's converted to shaft, right? Out. But we also have Q going out too, but we don't have to worry about that for efficiencies. Over here, that same shaft is going into the pump. Okay? And down below here where the water comes into the pipe, okay, we have mechanical energy or fluid energy coming in, and at the top here we have fluid mechanical energy coming out. That makes sense? Okay. What we're going to do over here we're going to assume basically that the water at state 1 going into the pipe was relatively 0. Okay, just for now, I could give you a speed, but we're just going to assume 0. And the point at the top in the tank, like the top free surface, okay, we're going to assume that's 0 for velocity. So the way we could tackle this is we can find the efficiency of this one, multiply by the efficiency of this one, or what can we do? We can combine these and we can get rid of the shaft. So one more sketch and then we'll get right to the solution. And I'm doing this on purpose to make sure you understand exactly how you can do this. So this is a combo. Which is pretty much what I drew up top. So let's get to the solution. And let's look at efficiency equation. And actually, we can look at both of these now. Oh, this is out. This is in. Over. Electric in. So the way we write this for these combos, especially for mechanical energy, is we subtract out minus in. Because what's that going to give us? Yeah, it gives us a delta energy of how much did we increase in mechanical energy, which is what's typically on the top here for efficiency, the general equation. Our output. Right? We want some sort of output with the electric coming in. All right. I like that purple. You guys like that purple? Yes. Yep. So I'll call it PM. Is that okay? Abbreviate it. Say that again. It didn't go anywhere. That's what I'm putting in right now. Kinetic, potential, and flow work. At state 2. Then we're going to subtract. Doing it this way, the long way, to show you every step, because if I don't, and I did it before when I first taught, students were confused. Okay, so I'm going through this detail by detail to show you where this all comes from and what we can do. So mechanical energy only deals with kinetic, potential, and flow work. There's no internal energy. All right? Questions so far? I'll review this when we're done too. We're at 10 minutes. That'll be fine. If we finish it Friday, we can finish it Friday. So let's go through. So these are all specific, right, inside here? And we multiply by that to get the increase in mechanical energy. Okay, we don't have any kinetic, right? We assume they're both 0. So that term's gone. And this term's gone. What about the pressure differences? They're the same. So those are gone. And where did I identify a datum? Typically your datum's at your first point. Okay, so 1. Wow, look at that.
Why is PE
we're assuming that's our datum. So Z1 is 0. Oh, I think I said Z1 is 0. Oh, I did. Okay, thank you. So this just becomes m dot PE2 over the electric. And do you remember what PE was? Is GZ2 over electric in. And we can rewrite m dot like this. Say that again? Yes, it was. It says it consumed so much, meaning we needed to supply that much energy. You want to plug this number in now? Did I do that? Yep. Wow, that was a crooked line. Density 1,000 kilograms per meter cubed times 70 liters per second times 0. How much time do I got left on my battery? 11%. We might do a pressure drop on Friday. That is a conversion from liters to meters cubed. Part B, the pump. Oh. Yep, we're finding the change in pressure. So we're only looking at the pump. So when we pick our boundary, we're just looking at basically where it's coming in and going out. Nope, you don't really need to. I mean, you could if you wanted to find the efficiency, right? But we're just looking at that right there. Yep. So here we can neglect PE and KE, just of the pump. Because the elevation change is very minimal, okay? No reason. Sorry. I can fix those. I didn't even catch that. Oh. There, to be complete. We're neglecting PE because the elevation change between those 2 points, even though pump is like this high, we're going to neglect those because it doesn't change much. And we're going to assume that the pipe diameter is the same, inlet is the same pipe outlet diameter. Okay, so the velocities are going to be the same, so we're going to neglect those. So there's really only flow work, which has to do with what? Pressure, right? All right, so how do we do this? Make sure I explain this right. So we're going to look for that. which we kind of have already, right? So I'm going to write this out again. At each of our new states, okay? So let's cancel some things. So we're neglecting these. And we end up getting m dot 0.2 and I'll rearrange this and we'll talk about some stuff. Yeah. So write that down. We'll talk about this. Then we'll sub the numbers. So we're looking at the fluid energy coming in and going out of the pump, so 1 and 2, and we're neglecting these two because the pipe sizes are the same for kinetics, so the velocity coming in is the same velocity going out. The elevation change is relatively small, so we neglect that. So when we look at this right here, this change in mechanical, oops, I forgot the delta down here. This change in mechanical energy is really the desired output of the pump, right? Because we wanted that pump to do what? Get the water from down, how far was Z2? 20 meters. So we want the pump to supply enough power to get it up to the top. So from part A, we actually found this term right here, the overall pumping power that we needed, which was m dot G times Z2. We could use that number in our calculation here to actually solve for delta P. All right, so this is actually equal to m dot G Z2 because it's energy, right? Which is the same energy that's going through the pump here, that the pump is actually supplying. Does that make sense? So again, the pump, we know how much power that's supplying. Our desired output of the pump from part A is this, because we need to get the water to shoot up 20 meters. That is energy. That same energy is then can be displayed inside this pump because it's conservation of energy. So if we look at the flow coming in and going out, then basically what's creating this power is this pressure difference. And we can find that pressure difference. Okay? So, let's plug our numbers in and find it. Whoops. Wrong button. Delta P. And I'm going to just plug this in. I want to do it this way. I don't think it matters. Did we find M dot? Or did we just kind of plug in the number? Plug the number. So, but we can kind of substitute what M dot is, right? Rho V dot G Z2 over V dot. And what happens to the V dots? They cancel, right? They should, right? Yeah, we'll make sure. Rho G Z2. So delta P is P2 minus P1, and the density was 1,000 times 9.81 meters per second squared times Z2, 20 meters. Yeah, 196 kilopascals. You can double check that calculation. So there's a lot of information given in this statement, in this calculation. What is the pump doing? How does a pump work? It's explained in here. What is a pump doing? Yeah, it's changing pressure. It's supplying energy, and it's creating high pressure at point 2. And where's point 2? Well, yeah, right at the outlet of the pump. So you have high pressure here. What does high pressure do? It likes to push things, right? So a pump increases the pressure so it can start pushing that fluid where it needs to go. Okay? So in our case, this pump had to increase the pressure by 196 kilopascals to get the water to go up 20 meters. That's what pumps do. Pretty cool, right? Make sense? Yes?
Is that point 2 is 20 meters or no?
Sorry, this Z2, this was from part A. So that 2 is actually 20 meters up, not the point at the pump. Sorry, I didn't mean to confuse you on that. Yeah. So just a few things again to remind you. When we find delta E mechanical, that is really our desired output of the pump. Okay? And that is energy. So we can find that amount of energy 2 ways, like we did in part A, or if I tell you the delta P, right? If I tell you the change in pressure, you can figure out how much energy is being supplied to that pump, right? You shoot that water up 20 meters. Okay. Questions? Hope this makes sense. All right, so solar energy reaching the Earth is about 1,000 watts per meter squared. A PV device can convert light into electricity with the efficiency of about 8%. Any alternative energy students in here? Are you taking? Yeah, that's right. You two are. Yeah, and you. Okay. So just a kind of a cool a fact about PV panels: 8% was actually good along like a few years ago. Now I think they're up to about 14 to 20% now, and they're written when you buy them, so you know. And the output that actually displays on the panel is correlated with that efficiency. It should be. I bought a whole set of PV panels and a solar charger connector at Harbor Freight for like $100, and it's actually worked pretty well. How large of a PV panel must one to obtain 2.5 kilowatts of power under ideal conditions? Find your answer. All right. So let's do this one. Given efficiency is 8%. Which is what in decimal form? Yeah, 0.8. 0.08. Let's do a sketch. Here's our sun. What color am I going to do it in? So bright you can't see it. Ha ha ha. No? Okay. I only laugh at my own jokes because they're stupid. Scarlett laughs at them. Makes me feel good. All right, and let's do our nice PV panel. Well, sort of a PV panel. We have bloop, bloop. So we have coming in, and what is it here? So we want two, so we have energy coming in, and we have energy going out, because we want to get 2.5 kilowatts. So what kind of energy is coming in? Solar radiation, yep. And then you have electric going out, okay? Just to let you know. So the out is what we're trying to get, 2.5 kilowatts, which is, move it over what, 3? 1, 2, 3 watts. And coming in per area is 1,000 watts per meter squared. See how I wrote that? Per unit area. That is a funny looking W. And I hope you're getting familiar now with W dot, Q dot, W, little q, little w. What else we got? Little v's, big V's. Okay, we're trying to find the area of the panel. Oh, it's not as bright. I can barely see the yellow on my screen. You can kind of see it. We had an instructor once that would use yellow chalk on a chalkboard. I think it was a green one. Yeah. Yep. Solution. It's like trying to use, let's see. Yeah, that color. You want that color. That's really bad. All right, so I'm going to start with the efficiency equation, because we know that, which is output over input. And I mean, there's a couple ways you can do this, but this is, I'll show you. We have W out, and then we have work in per unit area. We can multiply that by the area to get the actual work in, right? So I'm not sure how you would approach this problem, but this is the way I would have done it. I would have looked at the units and known that if I multiply that term by area, I can actually figure out how much energy is coming in total. And guess what that area is? The area of the panel. Why did I do that? That's what we're looking for, A. So I'm going to rearrange. So A becomes output over efficiency times W in per unit area. And we'll sub. So 2,500 watts over 0.08 times 1,000 watts per meter squared. And the area becomes 31.25 meters squared.